Good afternoon, welcome back. This will be our 39th lectures. We just have a few more lectures to go. So, as always, let me just run through an overview of what we did last time. So, last time we were on the topic of taking a deductive approach to finite fields, and then we started by talking about the characteristic of a finite field. We showed that it is a prime. We used that to show that the size of a finite field must be a power of a prime because it is a vector space over the ground field. After that, we moved on to the multiplicative structure of a finite field, and what we were able to show is that multiplicatively it has a very simple structure. All the non-zero elements are powers of a single element, and thereafter we showed that we moved on to talking about polynomials. We said we defined the minimal polynomial of an element as the smallest degree polynomial of which the element is a root. So, let me just begin over there. So, here is a definition of a minimal polynomial. It is the smallest degree polynomial of which the element is a 0. So, we were actually going through the theory of these minimal polynomials. What we actually proved is that the minimal polynomial of any element is irreducible. That is, if f beta is 0, then the minimal polynomial must divide it. And as a corollary, that m beta of x divides x to the q minus x. So, that is about where we were. So, we will continue on that today. I have called this subfields of a finite field, but actually this lecture is designed to take you to subfields and beyond. Okay. So, let us just see how far we can get today. So, the recap is we talked last time about the characteristic of a finite field, the multiplicative order, primitive elements, that is the element having maximal possible multiplicative order, and minimal polynomials. Now, we want to we would like to begin by saying a little bit more about minimal polynomials. So, first of all, let us define, and as I think in the past lecture, what I have done is, in the interests of making sure that I get through with a fairly complete discussion on cyclic codes, I have pre-written the slides. There is a small danger that I will go too fast. I will try to guard against that, try to slow down a little bit, but in any case you have the slides in front of you, so that should make it easier. Okay. So, let us get started. Now, I just quickly introduce some notation. We will use fq star to denote the non-zero elements of the finite field, and the first lemma states that, look, if beta is a non-zero element of the finite field, where q is a power of prime p, then the degree of the minimal polynomial of beta is less than or equal to m. So, this m is the same m that appears in this exponent. How do you prove that? Well, what you do is you consider successive powers of beta. So, 1 beta, beta squared, beta to the m. Now, there is a total of m plus 1 elements in here, starting from beta to the 0 through beta to the m. These cannot all be linearly independent, because supposing they were all linearly independent over what? Excuse me. So, what I mean here is linearly independent. So, we are actually thinking about the following picture. We have f p, and then we have f p to the m. Okay. So, we have a smaller field sitting inside a bigger field. So, when I talk about linear independence, what I mean is that I am going to regard this as a vector space over the smaller field, and I mentioned to you earlier that that is possible. So, from that point of view, there are m plus 1 elements in here, and they cannot all be linearly independent, because if they were, then the set of all linear combinations of these elements, that is where the AI, so let us emphasize that the AI come from Fp, the set of all linear combinations are all distinct, because that is a property of linearly independent elements. If any two are the same, that would imply a linear dependence relationship amongst the powers of beta, and we are assuming they are independent. But the total number of terms of this form, just you count the number of coefficients, there are m plus 1, and for each coefficient you have p choices. So, that makes for a total of p raised to the m plus 1. But that is impossible, because after all the finite field is only of size p to the m. So, the number of elements cannot be larger than that. So, the only conclusion we can draw from this is that this particular set of m plus 1 elements is not a linearly independent set. There is some dependency relationship amongst these elements. Okay. So, let us assume that that particular dependency expression takes on this form, that is the sum C I beta to the I is 0, with at least one of these coefficients being non-zero. But that is the same thing as saying that beta is a 0 of the polynomial C I x to the I. Okay. So, but then if that is the case, we know that the minimal polynomial divides any polynomial of which beta is a 0. So, in particular the minimal polynomial must divide this polynomial, but this polynomial has degree m. So, the minimal polynomial must have degree less than or equal to m. Okay. So, that is how the proof goes. Again, if you got lost in a little bit of the technical details, it does not matter, just keep in mind that if the finite field is of size p to the m and you take a non-zero element, its minimal polynomial is going to be of degree less than or equal to m. On the other hand, here is another lemma which says, well, that is true, but if this particular element beta is a primitive element, it is not just a non-zero element, it is a particular kind of non-zero element, it is primitive. That means every non-zero element in the finite field is a power of this beta. In this particular case, you can actually assert that the degree must be exactly equal to m. Okay, what is it that makes the difference? Let us say that the degree of the minimal polynomial of beta is s. Now, we already know from the earlier lemma that s is less than or equal to m, right. So, because we are dealing with the same finite field. So, the degree is less than the exponent in the size of the finite field. But since beta is a primitive element of the finite field, every element theta in the finite field can be expressed as a polynomial in beta, and therefore has an expression of the form theta equals the sum I is equal to 0 to s minus 1 a I beta to the I. Why is that? Well, the minimal polynomial has degree s. So, that means that beta to the s is dependent on lower powers of beta. So, we never have to cross an exponent of beta larger than s minus 1, because if we run into beta to the s, we can always re-express it in terms of lesser powers of beta. So, for that reason theta can always be expressed like this. But then the total number of elements here is only p to the s, because there are a total of s coefficients a I. Okay. So, again to emphasize that, let us just remind ourselves that the a I come from f p. So, the total number of elements of this form is p to the s, but since every element in theta in the field can be expressed like this, p to the s must be greater than or equal to m, p to the m, just by counting, and from that it follows that s is greater than or equal to m, but we just went through proving that s is less than or equal to m. Combining the two, we find that s is equal to m. So, again the result is easy to remember. If you are dealing with a primitive element in the finite field, its minimal polynomial has degree m, where m is the so called exponent in the size of the finite field. Just a definition that we will need to call upon later. The minimal polynomial m beta of x, so the notation stays the same, but for the cases when the beta is a primitive element of the finite field, then m beta of x is called a primitive polynomial, and we have already seen that primitive polynomials are of degree m. Okay, we just saw that in the previous lemma. Let us take an example. Supposing q is 2 to the 4, then the finite field of 16 elements, an example construction of that, we have seen this. You take the polynomials with binary coefficients and you reduce modulo the polynomial x to the 4 plus x plus 1. Okay. And this can also be expressed in the form f2 polynomials in alpha, where what we have actually done here is where alpha really denotes the equivalence class of x in this field. Okay. And thus, so let me just modify that to say where alpha equals this and thus satisfies. Okay, and thus satisfies this particular equation. All right. As seen before, so when we examined this finite field earlier, we remarked that this particular alpha is a primitive element. So that means if you take any power of alpha, let us say alpha to the k, then alpha to the k has order p to the m minus 1 divided by the greatest common divisor of k and the order of alpha, which is p to the m minus 1. So that in this case is 15 divided by the greatest common divisor of 15 and k. And from this you see that so what we are trying to get at here is what are some examples of primitive polynomials. Okay. So now the only way in which this thing could equal 15 is if 15 and k were relatively prime. So that means that if alpha is a primitive element, then the powers of alpha of the form alpha to the k, where this integer or exponent k is relatively prime to 15, these are the elements which are primitive in the finite field. Now, as an aside, it turns out that if you are given an integer which is the product of a power of primes, distinct primes, the number of integers L, where L is strictly less than n, such that L and n are relatively prime, is given by, so let us write this out in words just so that it's a little less confusing. Equals, and this function here is called Euler's totient function. So this is just a formula. So it says that if your original n is the product pi to the ei and you wanted to find the number of integers that's less than n and relatively prime to it, then what you do is you look at this factorization, reduce the exponents by 1, multiply by pi minus 1 and you get it. In our particular case, phi of 15 is the same as asking what is phi of 5 times 3, is 5 minus 1 times 3 minus 1, which is 4 times 2, which is 8. So what that means is that the field of 16 elements contains 8 elements that are primitive. Now, and those 8 elements corresponds to powers of alpha which are relatively prime to 15. So, and which are less than 15. So, the integers which possess that property are 1, 2, 4, 8, 7, 11, 13, 14. These are the 8 exponents k which are such that they are relatively prime to 15. So, these are primitive elements and there are 8 of them, and I have grouped them together in this particular fashion for a reason. The reason is that these 4 primitive elements share this minimal polynomial in common. These 4 primitive elements share this minimal polynomial in common. So, that is the reason for writing it out, for grouping them together like this. Thus, so in this particular field it turns out that x4 plus x plus 1 and x4 plus x cube plus 1 are the only primitive polynomials associated to this particular finite field. But as it turns out, all finite fields are really the same. So, this turns out to be true for all finite fields. So, I am just going to write this in brackets and just put down in here F16. Okay. All right. Now, the next topic. So, we are going to do a little bit of jumping around in the sense that there is a certain theory of finite fields that we will be using in the sequel, or else it is something that I feel that you should actually know. So, we will visit all these various aspects, and sometimes they will follow very nicely and continuously, but sometimes there will be a little bit of a jump. Okay. So, now we are making one such jump. We want to discuss subfields of a finite field. So, this is the situation when you have a larger finite field containing a smaller finite field. Okay. So, our goal, immediate goal now is to characterize all the subfields of a given finite field f p to the m, and it turns out that such a characterization is possible purely keeping in mind the size of the finite field. Okay. It is best illustrated with an example. When p is 2 and m is 12, then we are talking about the finite field of 2 to the 12 elements. It turns out to have the following subfield structure. It has this. So, here is the field itself, here is the ground field f2, and we already know of its presence, right. We know that every finite field contains the corresponding field obtained which corresponds to the characteristic of the finite field. So, we were already aware of these two. It turns out that the only other subfields in this finite fields are of size 2 to the k, where k divides 12. Now, the divisors of 12 are 6, 4, 3 and 2. So, they are all shown here. In this figure, whenever we draw a line like this, what we mean is that the element above contains the element below. Okay. So, f2 to the 12 contains or either by linked when linked by a single or multiple lines. Okay. So, it is also true that f2 to the 12 contains f2 to the 4, which contains f2 to the 2, and therefore, it is clear that f2 to the 12 also contains f2 to the 2. So, just by inspection you can see that containment simply requires that the exponents divide each other. For example, the reason f2 to the 12 contains all these fields is because these are precisely the divisors of 12. All right. You have 1, 2, 3, 4, 6 and 12 itself. And that is exactly what I have actually written out here, that the subfields are all of the form f2 to the k, f sub 2 to the k with k dividing 12. And this is not an isolated instance. It turns out that in general, whenever you have a finite field whose size is a power of a prime p, is of size p to the m, then the only finite fields that are contained inside it have size p to the d, where d divides m. Now, it is clear that any two finite fields must share the same characteristic, okay, because they share the same multiplicative identity. Any two finite fields with one contained in the other must share the same identity, and because they do, they must have the same characteristic in common, because you take 1, 1 plus 1, 1, and sooner or later a certain number of 1s will add to 0, and if it adds to 0 in the bigger field, it must add to 0 in the smaller field. Okay. So, therefore, whenever you talk about one finite field contained in the other, it is clear that the characteristic is the same. Okay. Now we are actually saying the only other condition that you really need to meet is that when you consider the size, the exponent of p must have the following divisibility property, that d divides m whenever this is contained in this. This is an if and only if statement. Now what I have done is I have actually skipped the proof of this theorem in the main text. The proof in complete form appears in the appendix. Okay, what do you mean by an appendix? Well, I took the liberty of putting towards the end of your lecture notes. So if you just go down, I've around the middle, a little after the middle, you will see a page 48 in my particular version, which says appendix, and this contains the proofs to the various theorems that appear in this lecture and whose proof is perhaps too long for us to go through at this stage. Okay, so let us get back to where we were. So basically this is the relationship necessary and sufficient condition for a finite field to contain a subfield. So again, making a short jump now, I am giving you a useful lemma and not really related to the previous discussion on subfields. And the lemma states that in any field of characteristic P, x plus y to the P is x to the P plus y to the P. How do you prove that? You just carry out the binomial expansion. So x plus y to the P is the sum I is equal to 0 to P, P choose I, x to the I, y to the P minus I. Now this, it turns out that there are actually P plus 1 terms in here, but if you work it out, only 2 terms, the 2 extreme terms survive, the others vanish, because if you look at this binomial coefficient P choose I, it turns out that except for the extreme cases when I is either 0 or I is equal to P, all the other values vanish modulo P, which means that because they are multiples of P. That is not hard to see, because if when you write it out, P choose I is P factorial divided by P minus I factorial times I factorial. So that is P into P minus 1 and so on up to P minus I plus 1, and then you have 1, 2 through I, and you can see that this is a multiple of P, okay, because all these others are P does not divide any of the others, and B being prime cannot have any of its factors contained in the denominator. So it follows that P divides this entire quantity, and hence when you go modulo P, this thing becomes 0. Okay. So that explains why you have a rather simple binomial rule in over finite fields of characteristic P. You just bring the P below. Next, going back to subfields of a finite field, what I have listed here is a test for membership in a finite field. Okay. So let us say that you have a finite field of size p to the m, and you have f p to the d which is contained in f p to the m. Then the theorem says that if you want to test for membership in a subfield of a finite field, so I should modify this a little bit. So I think let me do the following. I am going to write test for membership in a subfield. So the test simply says that if you want to know whether or not a particular element theta belongs to the subfield of size p to the d, then you just raise theta to the p to the d, dth power, and then you will get theta. Now, we know that if theta belongs to this field, then it must satisfy an equation like this, but this is saying that not only is this necessary, it is also sufficient. The proof once again is in the appendix. Okay, the proof is again written out completely in the appendix. What I think it is perhaps more what will perhaps help more is if I give you an example. So, let us say that f16 is f2 of alpha. This notation means the set of all polynomials in alpha whose coefficients lie in f2, where alpha satisfies the relationship alpha 4 plus alpha plus 1 equal to 0. Then in this field we know that f2 to the 4 is a subfield of this. Okay. Consider the subfield f2 to the 2. Consider the subfield f2 to the 2, and the test for this is to to verify whether or not it is true that x to the 4 takes you back to x. But x to the 4 equals x either can happen because x is 0, or else if x is equal to alpha to the k, because every element can be expressed as a power of alpha when it is non-zero, with alpha to the k raised to the 4th power giving you back alpha to the k. But that can only happen if alpha, this is now just alpha to the 4k, this is alpha to the k. So, the only way this can happen is if alpha to the 3k is equal to 1, but that is the same as saying that this k is either 0, 5 or 10. So, therefore, in this particular case the subfield test has led us to this particular set as being the subfield of the field of 4 elements, that is 0, 1, alpha to the 5 and alpha to the 10. Similarly, supposing now, so in this particular field that we are considering, you really have two subfields. You have f2, you have f2 to the 4, and then in the middle we have f2 to the 2. So, these are your subfields. So, we have already seen just now the test for membership in this particular subfield. How about membership in this subfield all the way at the bottom? Again you apply the same rule, because this holds for all these cases. It says that all that you need to check is that this exponent d divides this exponent m. So, the test is to check whether or not x squared is equal to x, but the only way x squared is equal to x can happen is if either x is 0 or else x is alpha to the k, with alpha to the 2k equals alpha to the k, that is when I plug in x equals alpha to the k here. But if alpha to the 2k is equal to alpha to the k, that implies alpha to the k is 1, which implies, but the only way this can happen is if k is 0. Okay. Therefore, the finite field, the elements in the subfield f2 are precisely those corresponding to x equal to 0 and the element x equal to alpha to the k with k equal to 0. So, 0 and 1 are the only two elements in the subfield. So, this is just verification, because after all we already knew that these two elements were in the subfield. So, if you put together this discussion that we just had, we have this picture, that is, you have the ground field, the parent field, and then you have this other subfield here, and these are precisely the elements in the subfields. So, you have 0 1 which belongs to the ground field, this is a particular subfield, and this is the entire field of 16 elements. Okay, now on to another mini topic. We have been proving several properties of a finite field, and I have shown you constructions of finite fields of size p to the d, provided a certain irreducible polynomial of a certain degree exists. So, the aim of this theorem here is to tell you that is to give you another way of showing that finite fields of every size of the form p to the m exist, as long as p is prime of course and m is greater than or equal to 1. So, what I have done here, I believe, is I have just sketched the proof here of this theorem, and I have left the complete proof to the appendix. Okay, so, you will find it at the back of your notes in full. So, the theorem says that finite fields exist of every size of this form, and when m is equal to 1, the set of integers modulo p z p is an example of a finite field of size p, and we are already familiar with that. So, there is no news in there. So, the more interesting case is when m is greater than or equal to 2. So, how do you construct finite fields of size p to the m when m is greater than or equal to 2? So, what we will do in this case is that we will recursively construct finite fields of characteristic p of increasing size. Okay, so, we are going to keep start with a finite field z p typically of characteristic p, and you keep building to it until we reach a finite field, until we reach a finite field that contains all the zeros of this particular polynomial. Then it turns out that this the collection of p to the m zeros of this polynomial form the desired finite field. Okay. And there is a little bit more to it than that. How exactly do you build finite fields of increasing size, but that is covered in the appendix. So, we will actually skip that. For us, it suffices to know that finite fields can only exist when they are of size p to the m, and if the size of if you give me a size p to the m, then I know that there exists a finite field of that size. Okay. So, that is what this theorem says. So, we are not very far from completing our discussion on finite fields. We need to wrap up the discussion on minimal polynomials and one other topic. So, this theorem gets us a start on that. So, it says that, so we are now back to discussing about polynomials. So, the polynomial x to the p to the m minus x over f p has the following factorization, that is, it is the product of irreducible polynomials. So, each of these f of x here is an irreducible polynomial. So, this is just saying that x to the p to the m minus x must be the product of a bunch of polynomials, of irreducible polynomials. But the interesting thing is that there is a lot of numerology in this, because it turns out that every irreducible polynomial whose degree is d for any divisor d of m appears here. So, for example, m could be 12, and you would have all the irreducible polynomials of degree 6, degree 4, degree 3, degree 2, degree 1, all of them actually appearing in here. Okay. So, that is interesting. And what we will do is we will actually illustrate by example, and the proof once again is sent back to the appendix. So, in the example we have that q is 2 to the 4. So, p is the prime p is 2, and then it turns out that when you factor x to the 2 to the 4 minus x, it factors as follows, and we already know from what the theorem says that it factors into the product of irreducible polynomials of degree d, where d divides p to the m. But it turns out that there are no other polynomials, irreducible polynomials of degree d dividing m. We will show that a little later. So, right for now we have that it factors like this. So, it turns out that these are the three irreducible polynomials of degree 4, these are linear of degree 1, and this is degree equal to 2. Now, the next theorem states that, and I mentioned this before, any two finite fields f q and f q prime are isomorphic provided they are of the same size. So, what does isomorphic mean? Isomorphic really just means that they are the same, except that what I call alpha you might call beta or beta cubed or whatever. So, up to relabeling they are really the same. There is a more formal definition of isomorphism, but in this finite case this will suffice. Also, the mapping from one finite field to the other, this mapping that I have just talked about will respect any algebraic relationship that pre-exists amongst the elements of the fields. Okay, here is a sketch of the proof. Let us say that alpha is a primitive element of f q and m beta of x its minimal polynomial. Then we know that m beta of x divides x to the p to the m minus x, right, because all the elements of the finite field of size p to the m are zeros of this polynomial, and that also applies to beta, and therefore, it must be that the minimal polynomial divides this. So, there are two finite fields here, f q and f q prime. So, what we actually did here was we started with f q and we picked a primitive element, identified its minimal polynomial, noted that it divides x to the p to the m minus x. Now, we move over to the other finite field, which is f q dash. In this field, every element is a 0 of x to the p to the m minus x. That was true even in the case of the other field, of course, and also is true here. Therefore, some element theta must be a 0 of this polynomial m beta of x. Then the map phi which sends beta to theta. Okay, what is beta? Beta is okay, so this is not yeah, sorry about that, that should of course have been beta. Okay, now we want to actually show that the two fields are isomorphic, but we know that in both fields it is true that the elements can be expressed in terms of linear combinations of powers of beta. Okay. Well, beta is the primitive element of the finite field. So, every element must have expression in terms of a polynomial like this, and now we consider the map between this element and the corresponding element here, the only difference being that you replace beta by theta. Okay. Remember, the tie between the beta and the theta is that they both share the same common minimal polynomial. Of course, it goes without saying that the AIs belong to FP. So, it can be shown that this is an isomorphism. So, just to emphasize, let me write here that what we have on the left is the finite field FQ, what we have on the right is the finite field FQ dash. So, we have established a map that goes from one finite field to the other, and the way that it works is that it takes every polynomial here in beta and maps it to a corresponding polynomial in theta. Now this can always be, this can in general always be shown to be an isomorphism. What we do here is we illustrate with an example. So let q be 2 to the 4, and then we note from this factorization, I have shown you this factorization earlier, that there are 3 or at least 3 different, well, we showed a short while ago that x to the 2 to the 4 minus x is really the product of all the irreducible polynomials whose degree divides 4. So that means that all the irreducible polynomials of degrees 1, 2 and 4, because 1, 2 and 4 are the only divisors of 4, all appear here. There are no other irreducible polynomials. So it is interesting that by factoring a single polynomial, you can with finite fields recover all irreducible polynomials whose degree divides your original, whose degree divides this particular polynomials, the exponent here, that is 4. Thus in particular there are 3 different irreducible polynomials of degree 4, and those are these 3. Now we want to show that the two fields are isomorphic, and it will help us if we actually regard these fields in the following way, that is f q is f 2 to the x modulo a certain polynomial, and f q prime for example could be f 2 to the x modulo x 4 plus x plus 1. Anyway, there are these two finite fields, let us say. Let beta be the equivalence class in f q, so that beta m, the minimal polynomial of beta, is x 4 plus x cubed plus x squared plus x plus 1, okay. Because the reason being that we already know that this is an irreducible polynomial. So if any element in the finite field is a 0 of this polynomial, then that element must necessarily be then this polynomial must be its minimal polynomial. So that is what I have written here. Similarly in here, let alpha represent the equivalence class of x in this field, then the minimal polynomial of alpha is x to the 4 plus x plus 1. So you can see that apparently these two fields are different, but it is not really so, because in f q we have already identified an element whose minimal polynomial in this. So let us first try to, in this second finite field, let us try to find an element whose minimal polynomial is this. So for that what we do is we have to identify an element in this second field which has this particular minimal polynomial, and it turns out that there are ways to do it. For example, you can show that if theta is alpha cubed, okay, then this element theta has minimal polynomial which is exactly this minimal polynomial of beta in the first field, okay. So okay, you have that. Now how do you, now what do you do next? Well, what you do is you just say, well look, this what you call beta, maybe what you call beta and what I call theta are the same. Already we know that they have the same minimal polynomial. So why don't we try the map from f q to f q1 in which we send beta to theta, and it turns out that that is an isomorphism, okay. So the elements are really in one-to-one correspondence, and so what that means, and above that it also respects the field operations. So really the two fields are the same, except as we have just noticed, what you call alpha in one, alpha or beta in one field is the theta in the other. Apart from that there really is no difference. Now on a more computational topic, I am going to introduce something that is called the add-1 table. It is also sometimes called the Zec logarithm, but that sounds too complicated a name for what it is. And as it turns out, the origins of the term Zec log are not really clear. So, we will just stick to the simpler terminology add-1 table. So, what this is all about is the following. It turns out that finite field computations are greatly simplified by the creation of an add-1 table. So, we present an example here. Let us say P is 2, Q is 2 to the 4 and Fq is F2 of x modulo x4 plus x plus 1 with alpha equal to x, so that alpha 4 plus alpha plus 1 equal to 0. So, this scenario is familiar to us, we have used this several times already. Okay. We also know that this particular finite field, that alpha is primitive in this field. So, that means all the elements in the finite field either correspond to 0 or else to some power of alpha for I lying between 0 and 14. And some lectures ago we looked at the polynomial representation of this finite field, in which every element in the finite field is expressed as a polynomial in alpha. And you can see that because we know that every element is a power of alpha, and this time the requirement is that and this time we are just representing everything as a polynomial in alpha. And with the aid of this polynomial representation, so the way in which we are going to use this table is as follows. So, I am interested in things like, here is alpha to the 4, it is alpha plus 1. What will I get if I add 1 to alpha 4? 1 plus alpha 4 is alpha plus 1 plus 1, the ones cancel leaving you alpha. Okay. So, that means that 1 plus alpha to the 4 is alpha. Similarly, if you add 1 to alpha 14, well, alpha 14 itself is alpha cube plus 1. So, alpha cube plus 1 you want to add 1 to it, then that will get you back to alpha cubed. Okay. So, in this way, with the aid of that other table, you can set up this table over here. This is called the add-1 table of the finite field, and it tells you that, for instance, that if you take alpha squared and add 1 to it, you will get alpha to the 8. Of course, the converse is also true. If you take alpha to the 8 and multiply it by a power of alpha, then the reverse is also true in the sense that if you take alpha to the 8 and add 1 to it, you will get alpha squared. So, similarly, alpha 3 plus 1 is alpha 14 and alpha 14 plus 1 is alpha 3. Okay. So, there is that symmetry. And how do you actually go about using this add-1 table? Well, you use this in conjunction with a method that is called Horner's method. So, here is Horner's method. So, Horner's method is used when you want to add a string of powers of alpha. In other words, you want to add several elements in a finite field and you represent them as powers of alpha. Of course, you ignore the zeros, and next what you do is you order them according to increasing powers of alpha. So, in this particular case, although it is not shown here, this was reordered according to alpha plus alpha cubed plus alpha to the 7 plus alpha to the 8. So, after this reordering, so we go there and then we come here. So, now in Horner's method what you do is you take the alpha common, then you get 1 plus alpha squared. So, that covers this term. Then you take that whole alpha cubed common and you get 1 plus alpha 4, and then you take alpha to the 7 common, you get 1 plus alpha. Okay. So, it is just a different way of representing this. If you multiply this all out, you will get exactly this, and I think if you are not convinced, you should try that out on your own. Now, once you have written it out, this is set up so that you can recursively use the add-1 table. So, for example, here 1 plus alpha is alpha to the 4, alpha to the 4 times alpha to the 4 is alpha to the 8, 1 plus alpha to the 8 is alpha squared, alpha squared times alpha squared is alpha to the 4, 1 plus alpha to the 4 is alpha, and alpha times alpha is alpha squared. So, that is your final answer here. Okay. So, in a way what you are really saying is that, look, if I want to think about my finite field, I can either think of the elements as polynomials in a primitive element alpha, or the other way in which I can actually think about the finite field is as powers of a primitive element alpha. And clearly the representation as powers of a primitive element alpha is so much easier and more convenient. The only problem is how do you add, because in the polynomial notation it is easy to add, in the power of alpha notation it is easy to multiply, because alpha cubed times alpha 4 is alpha to the 7, and that is obvious. So, you get in some sense the best of both worlds, because you get to work with the powers of alpha, and all that you need to do, there is only one cost involved, is that you need to keep this add one table in your mind. So, you either memorize it or have it on a sheet in front of you as you do the computations, and then the finite field representation is and then finite field computations become rather straightforward. Okay, we are edging towards the close of our lecture here, and our next topic, so again there is a little bit of a jump, is called cyclotomic cosets. Okay, what does that mean? The moment you hear the word coset, you start thinking, well, maybe this is talking about groups and subgroups, and the answer is yes and no. Okay. But why are we interested in these cosets? Because these cosets will be used to explain the structure of the minimal polynomial, and it also turns out interestingly to be helpful in constructing cyclic codes, that is error correcting codes for particular type known as cyclic codes. There these cyclotomic cosets will prove quite useful. So, the definition goes as follows. So, let P be prime, m greater than or equal to 1 as always. Then if alpha is a primitive element of f p to the m, then all arithmetic in the exponent of alpha is conducted mod p to the m minus 1, right, because supposing alpha has order 15 and you want to talk about alpha raised to the power k times l, then that k times l multiplication, you can regard that as modulo p to the m minus 1, because simply because alpha to the p to the m minus 1 is 1. Okay. So, for example, if I look at alpha to the p to the m plus 2, then I know that that is just alpha squared, and I can see that by doing arithmetic modulo p to the m minus 1 in the exponent. So, with that as motivation, what we do is we now focus on the set of integers modulo p to the m minus 1, and here we define two elements a and b to be equivalent if a is some power of p times b, and of course this is in this arithmetic is here in this algebraic structure. So, it is modulo p to the m minus 1. Now, you can verify this to be an equivalence relationship, and the resulting equivalence classes are called the p cyclotomic cosets mod p to the m minus 1. So, the reason why it is called p cyclotomic cosets is because the p appears here, and modulo p to the m minus 1 is of course I have already explained. Now, I have called this an equivalence relation. Okay, why is that the case? Well, that is because you can actually verify that the reflexive, the symmetry and the transitive properties actually hold, and I will not actually, although I have written them out on this slide, I am not going to bother going through them because they are elementary. So, it is clear that the reflexive, symmetry and transitive properties hold. So, this property that we defined here is an equivalence relationship. Let us illustrate with an example. When p is 2 and q is 2 to the 4, then the two cyclotomic cosets mod 2 to the m minus 1 are shown here. So, the cyclotomic cosets themselves are the resulting equivalence classes, and you will notice that the equivalence classes are of different sizes. Okay. So, each row here, therefore, in this diagram each row here corresponds to n. So, for example, this thing here is the equivalence class containing 3. Okay. So, similarly, there is another equivalence class which only contains 0. And it turns out that these are really not cosets, because if you were taking a group and a subgroup and looking at the cosets of the subgroup, you know that all cosets are of the same size. So, these are not really cosets, although there is a link with subgroups, but again for lack of time I will not pursue that. So, just accept the terminology cyclotomic cosets. Okay. Now, I think this is a good place to stop. We have covered a lot of ground, but I think given that the notes are written out and you have them accessible, you might just want to go through them once on your own, just to make sure you understand everything. We are almost completed with our discussion on the finite field, and in the next lecture we will actually start discussing cyclic codes. Okay. So, with that I will close. Thank you.